Hi, this is our superstructure design project. We are group number 3. Here's our group members. The members and connection of industry building and shades are different. For well system, the members and connection mainly includes well girds, columns, well bracing, fly bracings, and well claddings. And the connection method can be pinned or fixed. In our design, the connection method is pin. For roof system, members and connections mainly include rafters, purlins, and roof sheeting. The most common way is bolting the members. In the apex of the roof, rafters can be connected by apex brackets. To connect the rafter and column, hunch bracket, knee brace, and inner hunch bracket can be used. Load is one of the significant elements when designing. Table 1 shows application of loads in different parts of domestic building. Assuming the loads, for example dead load, live load, and wind loads, is carried out from the apex area, the load path will start at the roof sheeting. Then the sheeting transfers the loads to the purlin, which is supported by rafters, truss, and steel beams. To prevent shaking of the roof system, roof bracing can be applied. Well system is used to carry out the whole loads from the upper part of wells or ceiling rest. The column as a compression member is designed to resist lateral forces. Girds as a horizontal structure member is also designed to resist lateral forces, especially wind load.
Next, we are talking about the site visit at Mossam Lakes. And here are some photos of outside of the site building. From these pictures, the building is an industrial building with metal panel external cladding. Moreover, there are large and small entrances which are designed for human and vehicles. This action will ensure safety of human and improve efficiency. Next picture shows the connection of walls and roof. To connect them, there are many components which are needed. For example, in this picture, purlin, rafter, and column. The insulation coated on purlins which connected with rafters, and the load of insulation is transferred through purlin to rafter. Besides, each rafter connects with one column and transfers load to them. Finally, the columns carry loads to the footing. Moreover, the bracings of rafters and columns are used for carrying the wind load. In this property, bracings should have been structured as cross bracing instead of single bracing to bear both directions of wind load. And here are two pictures show the details of joint of column and rafter in the corner of the building. The next picture illustrates the components of walling system, which are column, gird, flat bracing, and insulation. Flat bracings which connect columns and girds to prevent them from twisting and rotating while under load. Girds can fasten the wall cladding and provide shear resistance. The next one is roofing system. And in the first picture, which is the flat bracing in the front side, purlins are placed in equal spacing, and roof cladding can be fastened on them. Flat bracing connects rafters and purlins appear in picture 1, but they are not placed on the other side of rafter shows in picture 2. This is a mistake of design structure because bracings should bear both directions of wind. And here are two pictures to show the appendix bracket to connect rafters. The last picture of site visit is detailed column and gird connection. This picture illustrates how girds connect with columns. Most of girds are bolted to the columns, and some of them are connected by fly bracing to prevent twisting and rotating.
Now come to purlin design and gird design. Purlin and gird is similar. A purlin is a horizontal member which carries roof slag or roof sheeting load and is supported by rafter, trusses, and steel beam. Gird is a horizontal structural member in a frame wall. Gird provides lateral support to the wall panel, primarily to resist wind load. There are different kinds of load applied to a purlin and gird. When we design purlin, we need to apply dead load, live load, and wind load. While we design gird, we do not require to apply dead load and live load, but only wind load. A key consideration when choosing a profile is roof pitch. Thin deck is selected for our design project, as our project has a 3-degree roof pitch, which meet its requirement of minimum 2-degree roof pitch. Other considerations include architecture style, market available, mass and price, and the last one, which is limitation of support spacing. Table provides a maximum recommended spacing of support 2.6 meters for purlin and 3 meters for gate. As our project, we allow 2.6 meters for purlin spacing and 2.5 meters for gate spacing. A larger spacing requires lesser purlin and bigger section of purlin. The picture shows the number and spacing of purlin and gate that we had designed for our project. There are two common sections for purlin, which is Z purlin and C purlin. The advantage of Z purlins can be lapped in continuous span and increase the capacity. However, C purlin cannot be lapped. It is being used continuously over 2 or more spans, thus producing reduced deflection. Continuous length of purlin results in better economy, that lapping increases the strength of the section where bending moment and shear are at a maximum, thus improving the load capacity and rigidity of the system. For our project, we have selected double continuous span because it is more economical. Bridging is a tension member used to limit the deflection of a purlin in the direction of its weak axis. As picture shows, X is the strong axis and Y is the weak axis. According to the capacity table, Z224 is selected with a 2 rows of bridging in each span to limit the deflection of a purlin.
Bracing design is to carry all lateral load from horizontal roof bracing to vertical bracing and then foundation. As bracing are used to transfer the lateral load in both directions, we should design the roof and wall bracing in each direction separately. As diagonal members are to resist tension only, we have to remove the compressive diagonal members based on the position of load applied. As vertical bracing are the supports of roof truss, the reaction of horizontal truss is lateral load for design of vertical bracings. All diagonal members will be designed as equal angle for maximum tensile load, while roof truss will use circular hollow section for maximum compressive force. In our project of column design, which are beam column collections in a braced frame, so we consider the load eccentricity as beam column joints causing bending moments. Due to different supporting area of column, intermediates and end column are designed separately. Firstly, we have to calculate the dead load, live load, and wind load in order to determine the load combination for maximum compression and tension force. We will select a suitable universal column for compression capacity based on maximum compression force. Then we check this section of universal column for moment capacity by working out the bending moments on top of the column. We further design the column for the combination of compression and bending moment by using the equation. Finally, we check the select section for reversal action with maximum tension force.
Rafter design. When we design intermediate rafter and end rafter, both have different supporting area of beam. Intermediate rafter tend to have a larger supporting area of beam than end rafter. Assumptions have to be made whether it is a maximum bending moment in a simply supported beam with a concentrated load at the midspan or uniform distributed load. For our project, we also use fly bracing to restrain the bottom flange of the rafter and prevent from lateral torsional buckling of the rafter.